Alright, in this video we're going to talk about approximating polynomials by recentering. And this isn't a standalone topic, it's going to lead us into Taylor's series, so this is a precursor for that. I picked a polynomial, I wanted the degree to be kind of high, so it's degree 5, I wanted the coefficients to be ugly, and you can see that even though it's hideous, when we plug in 0, it's pretty clear what we get. We just get that constant term, negative 18, right? So that wasn't bad. Now, next, we'll try, instead of plugging in 0, to plug in something close to 0. Let's try 0.1. So when we plug in 0.1, I'm just going to throw this in my calculator. I'm not going to do it out by hand. And I'll get negative 13.83916. That's a hideous number. We can all agree on that, I think. But now, what if I had gotten tired typing this into my calculator? And instead stopped after the x squared term? Well, then I would have gotten negative 13.89. And that's actually really close to what we had gotten before, right? So it's not until we get to the hundredths column that this starts to differ. So we have the same polynomial. Let's go ahead and try what happens at x equals 1. Right, when I plug in x equals 1, I get negative 4 for this polynomial. And if I go to the x squared term, what does that do? Well, I get negative 39, and that is not as close as before, right? It's way far off. So what's going on? Was what happened at 0.1 a coincidence? You can see when I plug in 0.1 into the polynomial, what happens when I square and cube and take 0.1 to the 4th and 5th? What is that doing? Well, these later terms are very small, right? So they matter less. That's not the case when I'm at x equals 1. But what happens if I want to approximate this polynomial near x equals 1? What's going to go on there? So we have this same polynomial, and because it's so easy to find p of 0, I'm going to call the polynomial, when it's written in this form, p of x centered at 0. Because it's so easy to find that value when x equals 0. When I write this polynomial out like this, I'm calling it p of x centered at 0. And when I want to specify that I mean this form, I'm going to give it a special notation, p of x semicolon 0. And so more generally, for any polynomial, the polynomial centered at 0 has this form. So the constant term plus a number times x to the first, plus a number times x to the second, plus all the way up to a number times x to the n. And these qi's that I've written down, they're just numbers, right? But anytime I have it in this form, I'm going to say it's centered at 0. And I'm using this notation because it generalizes. So I can also talk about q of x centered at a. And by that, I mean it looks like this. And I'm using q tilde and m just because I don't want them to be the same. So I had this form before that was centered at 0, and now I have this new form. Now pay attention, the qi don't have to be the same as the qi tildes. That's why I gave them different names. But if, in fact, they often won't be the same. But if the coefficient of the highest power of x and the coefficient of the highest power of x minus a, if they're not 0, then n is equal to m. Then the degree of one is equal to the degree of the other. So the degree of these two polynomials, because they're the same polynomial, when you multiply them out, they're going to have the same degree. And so I'm going to, in the next video, ask how can we find a polynomial centered at a different value starting from the polynomial centered at 0. And just a hint, to get you thinking about it, it involves their derivatives.